Hello everyone, today I have a pretty cool piece of mathematical trivia. Every odd integer is the difference of two perfect squares. Now what do I mean by that? Well, we can say that 5 is equal to 3 squared minus 2 squared. You can check that yourself. Let's see, let's pick another odd integer. 11 is equal to 6 squared minus 5 squared. Simple enough. Let's try one more. 15. Well, that's just equal to 8 squared minus 7 squared. So you can check all these and you'll realize, wow, these are all correct. Now what's going on here? Why is this happening? Well, think about it like this. We can factor this difference of two squares, right? We could say that 3 squared minus 2 squared is just 3 minus 2, which is 1, times 3 plus 2, which is 5. So this is giving you the 5 and this is giving you the 1. And when you multiply these together, you'll just get 5. Same for this and this. You get 6 minus 5, which is 1, times 6 plus 5, which is 11. And you get 8 minus 7, which is 1, times 8 plus 7, which is 15. But what's really going on here? Can we actually prove this type of thing? Can we prove it in another way, algebraically? Well, let's try this. Let's say that there's an odd integer, 2k plus 1, for a k that is an integer. So that means that k is an integer, a positive integer. We'll just keep that simple for right now. We'll just say it's a positive integer. And then this right here is an odd number. Now, why is this an odd number? Well, 2 times an integer will always be an even number. And when you add 1, you're always going to get an odd number. So you got 2k plus 1. Now, let's see if we can try to shape this into a difference of two squares algebraically. Okay, I can't really think of that much now. However, think of it like this. 2k plus 1 can be split up like this. K plus 1 plus k. Now, when you look at this, you kind of see, you got k plus 1 over here, and you got k over here. Maybe you can use that to your advantage somehow. And the answer is you can. Think of it like this. We can now move from this step to this step, where it's a minus b times a plus b. Why is that? Well, let's pretend k plus 1 is a, and k is b. Well, in that case, a minus b would just be k plus 1 minus k, and I'll just write it like this, k plus 1 minus k, and then a plus b, k plus 1 plus k. So as you can see, k plus 1 minus k, and then k plus 1 plus k is equal to 2k plus 1. Now, notice this, k plus 1 minus k, well, that's just 1. And this right here, k plus 1 plus k, well, I mean, that's just 2k plus 1, right? So we're kind of going backwards here, but I just want to make sure you realize this 2k plus 1 is pretty much k plus 1 minus k times k plus 1 plus k. And when you multiply these together, you get back to 2k plus 1. So going back to this k plus 1 minus k times k plus 1 plus k, well, let's go from this step to this step, the actual difference of two squares. So we get k plus 1 squared minus k squared. And that completes it. We get 2k plus 1 is equal to k plus 1 minus k times k plus 1 plus k is equal to k plus 1 squared minus k squared. And that was the algorithm I was using myself when I was calculating the difference of two squares, which squares we needed to get that odd number. So if 5 was 2k plus 1, then that means k is equal to 2. So that means you get k plus 1 squared minus k squared, so 2 plus 1 squared minus 2 squared, 3 squared minus 2 squared. Same thing for 11 and 15. Now, we got this kind of like make common sense type of thing. We got this quote-unquote proof right here. But, it should still be a little confusing. Why, though? Is there some type of drawing we can do, some type of geometric interpretation that I can make of this certain fact, a certain piece of trivia? Well, yes. And that's what we're going to do now. finally I'm going to present this last geometric proof that really will solidify your understanding of this idea right here. Let's say I have 5 dots. Drawing it right here, 1, 2, 3, 4, 5. So I just drew 5 dots. Now I want to bend it so it looks like this, like this, like a backwards type of L, up and to the right. Now how do I do that? And I want both sides, this side and this side, to be the same. So how do I do that? Well, I have to make sure that the number of dots over here is the same as the number of dots over here. But we can't necessarily do that because it's an odd number, right? However, we can have one be a corner, one dot be a corner. So we have 2 dots horizontally, we have the corner, and then 2 dots vertically. So we went from this horizontal line to this right here. 1, 2, 3, 1, 2, 3. Up, right. So now that we have this, what does this remind me of? Or what does this remind you of? Well, it reminds me kind of a square. You got a 3 by 3 square over here, but it's incomplete. You got this dot, this dot, this dot, and then the middle dot. But let's just say that this was a whole square. This was 3 times 3, 3 squared. Now, 3 squared is equal to 9, not 5. So we have to subtract some number to get 5. Now, what do we subtract? Well, we still have this dot missing, this dot missing, this one missing, and this one missing. Essentially, the next layer. We're missing the next layer of the square. We're taking that part out. And so we're taking out, let's see, 2 by 2. 2 times 2, or 2 squared. So as you can see, we can write 5 as basically a 3 by 3 square, but taking out the next k minus 1th square from it to get an answer of 5. So I hope this geometric proof can help you. To practice, you could just try some other numbers. You can try 3 to make it really easy. You can try 7, 9. Again, you can try any odd integer. That's really the beauty of this idea. And anyway, that's a good place to stop.